So we will start with divergence today. So so far we have seen convergence sequences, of course, and they are well behaved members of the family of sequences. Today we will see the moderately and ill behaved members of the family of sequences, and they together are called divergent sequences. So divergent sequences are obviously, as the name suggests, they are not that easy to work with, easy to deal with. They are moderate behavior or mostly ill behavior. We will make precise mathematical definitions of these vague ideas. What do we mean by moderate and ill behaved members? So let us proceed to that. Now, by definition, a sequence of real numbers is divergent if it is not convergent. As simple as that. All sequences which are not convergent are called divergent. Okay? So, examples, the sequence of natural numbers is a divergent sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 goes on. This sequence of natural numbers is a divergent sequence. Fine. The sequence minus 1 to the power n, that is minus 1, plus 1, minus 1, plus 1, minus 1, plus 1. This sequence is a divergent sequence because it is not a convergent sequence. As simple as that. The sequence n to the power minus 1 to the power n. This is a divergent sequence. All these examples, what I am giving you, these examples we have already seen in the in the first lecture when we saw all these examples and all. So these examples I am taking from there only. So the sequence n to the power minus 1 to the power n, where this is the sequence. So this is how it goes. X1 is 1, x2 is 2, x3 is 1/3, x4 is 4, x5 is 1/5, and so on. Fine. So the set of all the divergent sequences is a mixed bag in the sense that there are some sequences which diverge to infinity, plus or minus infinity, both. I mean, not at the same time, but some sequences which diverges to plus infinity, some sequences which diverge to minus infinity, and so on. Like the sequence of natural numbers, the first example, they are these guys are moderately behaved members of the group, the diverge to infinity. Now the other members of the group are ill behaved. They are called oscillating sequences, like minus 1 to the power n. In the second example, like the third example, n to the power minus 1 to the power n. So they are ill behaved members. Out of these two sequences, this minus 1 to the power n, minus 1 to the power n, and n to the power 1 minus 1 to the power n, out of these two sequences, the first one, minus 1 to the power n, is an example of finitely oscillating sequence, whereas the other one is an example of infinitely oscillating sequences, the worst chaps of the entire family. So these are the infinitely oscillating sequences are the worst chaps of the entire family. So you see the graph here. This is the graph of in minus 1 to the power n over here. So this is minus 1 plus 1 minus 1 plus 1. So there is a finite oscillation going around over here. So they are oscillating within a finite bound. But over this one, n to the power minus 1 to the power n, this guy over here is not oscillating within a finite bound. This is at 1, this is at 2, this is coming at 1/3, but this is going at 1/4, this is coming at 1/5, but the next one will go at 6, the next one will come at 1/7, but next one will go at 8. So this thing is, I mean, going bigger and bigger. So to control them is extremely hard. So that is why these are the worst members of the entire family. So I'm just trying to give you the sense that which is, I mean, easier to handle, easier to work with, and why is the case. So how do we handle these worst chaps, worst members, ill-behaved members of the family? That we will get to know after today's class, at the end of today's class. So let us see the formal definitions first. So here, oscillating, finitely oscillating, infinitely oscillating, all these things we have just defined with our common sense of understanding. And so let us define these terms formally. Now, the first definition is a sequence diverging to infinity. Now, whenever I am writing infinity in word, I mean plus or minus infinity. Whenever I'm writing in a notation, in mathematical notation, I'm putting a plus or minus in front of that. So a sequence xn, a sequence of real numbers xn is called diverging to infinity, plus infinity, if, understand the definition, for every for every number g positive, there exists a natural number threshold term index k, such that for all terms greater than that, after that threshold term index, xn exceeds g. Okay, and this is the definition of diverging to infinity. This is the definition of diverging to minus infinity. A sequence is called diverging to minus infinity if for all positive number g there exists a k such that for all n greater than equal to k, xn is less than minus g. Okay, so we'll understand these definitions in a little bit. First, let us see some examples. The sequence of natural numbers n that diverges to infinity, definitely. The sequence of negative integers, this is the sequence of positive integers, this is the sequence of negative integers that diverges to minus infinity. This sequence xn, where xn is this thing, 1 plus half plus 1/3 plus up to 1 by n. So this is the sequence of harmonic means. This sequence diverges to infinity. You know this result from, if you do not know this result from the chapter of sequences, I guess I know you must know this result from the chapter of series, that this series diverges to infinity, and that from the definition of divergence, from the definition of convergence of series, the sum of series, this is the partial sum sequence. So this sequence also diverges to infinity. The sequence r to the power n diverges to infinity if r is greater than 1. Then the sequence r to the power n diverges to infinity. Fine. So let us see some remarks and understand the definition. To understand the last definition, we need to understand the concept of infinity a little closely. Okay? Infinity is not a number. It's a notation to denote the biggest number possible for your particular case. For example, if you are dealing with the particle distances inside an atom, the distance 1 meter is infinity for you. If you are concerned about speed of an electric car, the speed of light is an infinity for you. Infinity is a relative measure to denote the biggest upper bound to be considered for your particular case. Taking anything greater than that upper bound is simply not economical. So it is like, suppose you want to build a particular device to measure the distances, the atomic particle distances there. Now, every device must have a range, like just like the ruler inside your pencil box. That ruler has a range from up to 6 inches or 15 centimeters. If that ruler does not serve your purpose, there are bigger rulers to serve your purpose. So every device must have a range. So whenever you are manufacturing a device for measuring the atomic particle distances, the what should be your infinity there? what most distance can it should measure. It should not it is not necessary to make a device which can measure more than 1 meter. If the primary objective is to use the device to measure the atomic distances, atomic particle distances. So similarly, when you are making a electric car, you're making a motor vehicle, there, I mean, nowadays people have made engines which are extremely capable, extremely fast, but nothing can be more than speed of light, and that is also a extremely sort of glorified guess. And I mean that works for everything, not only this one electric car, but also for any moving object you want to make. So anyway, um, when you are making the speedometer of that car, you do not have to put that more than the speed of light, or more than say 2000 kilometer per hour, because a car can never reach that speed. So the your device, if it can measure from 0 to 2000 kilometer per hour, then it is enough. You do not have to put your resource to make a device which can measure from 0 to say 10,000 kilometer per hour, that range. That is simply not economical. Just look at the just look at the this thing, the what is that called, um, the weighing machines in the in the grocery store, and the and in a jewelry store. In the jewelry store, those things are made to measure very precise amount of precise amount of mass, precise results, and that varies from, let's say, 0 gram to 100 grams, not more than that. But the grocery machines, they cannot measure that precise things, but they vary from say 0 gram to 10 kilogram or something. So everywhere, whenever you are making a device, there is some range you need to consider. You cannot make from minus infinity to plus infinity, or 0 to infinity. That true sense of infinity is never ever possible to make in real life. So whenever you are making that highest upper bound, that highest upper bound is infinity for you. Nobody is coming with an 100 gram bar of gold to measure in a jewelry shop. So that part is not necessary. Why to I mean the manufacturer of a weighing machine in the jewelry shop does not have to make the instrument, I mean uh, sensitive to more than 100 gram of weight. So this is what I mean by infinity. Infinity is the biggest upper bound you need to consider. This is a relative measure of how big your thing can be. Anything bigger than that is simply not economical. That is what infinity for us. For infinity, for particle distances, 1 meter is infinity. For anything velocity, the speed of light is infinity. For a jewelry weighing machine, 100 gram is infinity. For a grocery weighing machine, maybe 50 kilogram is infinity, and so on. So the number g in the definition, in the last definition, this definition over g, uh, g is um, in the definition carries a silent tag, however big. Just like the epsilon in the definition of convergence, which carried however small tag, this over here, this G carries a silent tag, however big. Uh, this denotes how big your biggest number, that is your infinity, is. The definition guarantees that for whatever choice of the biggest number, So G is equal to 1 meter if you are making a device for atomic particle distances. G is equals to say 2000 kilometer per hour if you are making an electric car. Even G is equals to 100 grams if you are making a weighing machine in the jewelry shop. G is equal to 50 kilograms if you are making a weighing machine in the grocery shop. So that is your biggest number. So that whatever choice of the biggest number, the sequence will eventually become bigger than that biggest. So let me see the definition over here in this screen quickly. Yeah. So um, for all G greater than G0, so for all G however big, for all positive number G however big, that is how we are going to sense it from now on. There exists a term index K such that for all term after the term index, the nth term will be more than that infinity number, that biggest number. So it is bigger than the biggest. That is what we mean by diverging to infinity. Okay, so the number G in the definition carries a silent tag, however big. Just like epsilon in the definition of convergence, this denotes how big, I mean, just like the epsilon in the definition of convergence, it denotes the how small your error you want to be. Here, this denotes just how big your biggest number infinity is. The definition guarantees that for whatever choice of the biggest number, the sequence will eventually become bigger than that biggest. Next one, just like in the case of convergence, the rate at which a sequence diverges to infinity is something numerical analysts bother. The sequence xn, where this harmonic mean sequence 1 plus a half plus 1/3, this one diverges to infinity for sure, that we know from theory, but the first 10 to the power 43 terms, 10 to the power 43 terms cannot even exceed 100. That slow this number is. This sequence, the rate of divergence of this sequence is. Um, the entire above discussion can be carried out parallelly for the sequences diverging to minus infinity by replacing the sense of big by the sense of small, in the sense that negative infinity is the notation for the smallest number possible. So it is going towards right and going bigger and bigger. It is in the case of going to tending to minus infinity, it will be going to the left and being smaller and smaller. The sequences diverging to infinity are moderately behaved members of the family of sequences. Like convergence sequences, they head over to a particular direction for their entire journey, with only exception that the destination for their journey is not a very comfortable number to work with. But all of them are heading to a particular way only. Okay, they are not fluctuating that much. Everything is going to the same direction, either to plus infinity or to minus infinity. So that is why these are sort of moderately behaved members. So we know how do they behave. Just take on convergence sequences, we know that they converge to that number. They eventually become close to the limit, and we know that these things become close to infinity. And infinity, we know, we have now have a idea that it will become it will go away from whatever upper bound we set for them, or whatever lower bound we set for them in case of a sequence diverging to negative infinity. So that is something we know very well for this. So we know the behavior of the tail of a sequence, how is going to behave. It is going to be outside of our view in case of divergent to infinity of minus infinity sequences, or it will be converging to a certain limit in case of convergence sequences. So convergence sequences are definitely good, well-behaved members, and these are sort of moderately behaved members. Next up we have oscillating sequence. The definition of sequence diverging to infinity guarantees that if such a sequence becomes bigger than an arbitrarily big number at a threshold term, it stays bigger than that for the rest of its terms. Okay, so it is for all n greater than or equal to k, xn becomes more than xn stays more than g. Just like in the definition of convergence, for all n greater than or equal to k, the distance between xn and the limit stays less than epsilon for the rest of its terms. The whole tail follows the same way. Here also, for the entire tail will stay more than g for the the entire after this kth term onwards. And same will be the case, same but the opposite will be the case in case of negative diverging to negative infinity. So now over here, if that is not the case, then we get oscillating sequences. A sequence of real numbers is oscillating if it is neither convergent nor diverges to infinity. As simple as that. Oscillating sequences are neither convergent nor diverges to infinity. Examples: minus 1 to the power n is an oscillating sequence. N to the power minus 1 to the power n is an oscillating sequence. The sequence r to the power n for is an oscillating sequence for r is smaller than 1, smaller than minus 1. So r greater than 1, it will be this thing, um, diverging to plus infinity. R mod r within 1 smaller than 1 will be a convergent sequence, and r smaller than minus 1 will be an oscillating sequence. So depending on their behavior, oscillating sequences can be of two types. The first one is finitely oscillating sequence. A bounded oscillating sequence is a finitely oscillating sequence. So the sequence, this minus 1 to the power n is a finitely oscillating sequence. Here we have the thing over here. Yes, this is finitely oscillating, minus 1 to the power n, minus 1 plus 1, minus 1 plus 1, minus 1, this way. So minus 1 to the power n is a finitely oscillating sequence. And the sequence sine n is a finitely oscillating sequence as well. So sine is bounded between minus 1 and 1, and this is a finitely oscillating sequence. Next up, we have infinitely oscillating sequences. An unbounded oscillating sequence is an infinitely oscillating sequence. More precisely, a sequence of real numbers xn is an infinitely oscillating sequence if it is oscillating, and for any arbitrary g positive there exists k such that the kth term, the mod value of the absolute value of the kth term exceeds g. Understand this thing, that this does not stay more than g. It comes down after maybe at the k plus 1th term. So it does not stay. It is not saying that it stays more than g. It says that whatever number you give, we will have some term which will exceed that number. Okay, so that is why it is unbounded and oscillating sequence. So this is infinitely oscillating sequence. Examples: this n to the power minus 1 to the power n is an oscillating sequence. We have seen over here 1, 2, 1/3, 4, 1/5. Next will be 1/6. Next will be 1/7 over here, and so on. So this is an infinitely oscillating sequence. So give any number, let's say 1 billion. So 1 billion term will be 1 billion plus 2 term will be more than that number 1 billion. So this is an infinite oscillatory sequence. As you can sense that these sequences are most ill-behaved members among the family of sequences. To deal with them properly, we have brought in the concept of subsequences. So subsequences, the section on subsequences where actually, I mean, we people needed to think of subsequences to deal with this kind of guys, the most ill-behaved members of the family. That is oscillating sequences. Without the oscillating sequences in existence, the study on subsequences would not be necessitated.